Okay, still we are in the second module of this current electricity, and in the earlier session we uh, just talked about a word quantity, physical quantity, electrical physical quantity, that is current density. Just we talked about it very less. So in detail we'll learn about it today, and along with that one more important thing which is necessary for understanding this electric current, especially the current flowing in a conductor. Right, now let us talk about this electric density, current density. So there we define the current density as it is current density denoted by J. It is the electric current which is passing through a cross-sectional area. Let it be A I perpendicular to it. Mean that, so if the current is in this direction and the area what you are taking, this is perpendicular to it. Okay, so then this J is given by I by A. J is given by I by A. And you know that here your electric current is a scalar quantity. It's a scalar quantity, and J is a vector quantity. So I can just write J as J bar. Okay, if you write it or not, no problem, but just for practice, it's a vector quantity. Right, now if it is a vector quantity, what is its direction? J is in the direction of the electric field. That means your current density is in the direction of electric field. Suppose if you consider the positive, if the charge carriers are positive, and you are considering the positive charges, the moving positive charges, if it is positive, then your J will be in the opposite direction. And if you consider here the moving charges are negative, then your J will be, positive means it in the same direction, isn't it? Because it will be in the direction of electric field. It is in the direction of electric field, so it will along with the direction in which the positive charges are moving. If it is the negative charges, then J will be opposite to it. Your current density will be opposite to it. Okay, now from here you came to know it is J is equal to I by A. So the SI units will be I is in ampere and area is in meter square. So ampere meter square. This is the SI unit. That is the SI unit. So like this we can talk about the electric current density initially. Suppose if you consider a uniform conductor, whose cross-sectional area, uniform conductor means whose cross-sectional area is uniform throughout. Then if we talk about the I, this is uniform throughout. And in a similar manner, J, our current density, this is also uniform throughout. So this is for a uniform conductor. And we are talking about a non-uniform conductor. That means its cross-sectional area is not uniform throughout. Then here your I is uniform throughout. at each and every cross section of the conductor, the current flow will be, the flow of charges will be uniform. So thereby I is uniform throughout. But this J is not uniform. It changes from point to point. Okay, so just keep this in your mind. For uniform conductor, I is uniform throughout and J is uniform throughout the conductor. If it is a non-uniform conductor, I is uniform throughout and J is not uniform, but it changes from point to point. Okay, so after this, let us understand one more thing here. Suppose if a conductor is there, suppose if this is a conductor and this is the flow of charges, and if I is the current, and if your area is perpendicular to this current, then J is equal to I by A, as you know very well. But every time we cannot expect, or we cannot consider, or for our calculation purpose, we have to go with the area which is inclined to this. That means making some angle with the direction of the electric current. Inclined or making some angle with the direction of flow of charges, direction of electric current. Then, how can you show it in the form of a diagram? So if this is the direction of the current, and actually it should be like this, but now it is inclined at an angle. Inclined at an angle. So that means, so here, this is the part normal to the surface, isn't it? Now this is making some angle with this direction of the current. So this theta is the angle made by the normal to the surface to the direction of the flow. So that theta, if it is theta, that means if it is not perpendicular, then your J is equal to I by A cos theta. If current is small and area is small, delta I by delta A cos theta. Okay, so if it is inclined, we have to use this formula to go with it. Okay, so this is regarding the, what you call it as the useful information for your current density. Okay, so just pause the video and take the screenshot of this. Okay, after understanding this current density, we will move on to the next important thing what we are going to learn now. When the charges are flowing. So if you consider a conductor here, a conductor, now here already we know that initially, even if the potential difference is not applied, the charge carriers, that means it is having the availability of free electrons in it. So it will be having some free electrons in it, and their motion will be at random. We already know about this. So now, so these charge carriers, here are free electrons. And you know that what are these free electrons? These are the electrons which are not, which does not belong to any particular atom. Those are called as the free electrons. Now, these free electrons are responsible for the flow of charges in a conductor. So that's why we can call them as the conduction electrons. Conduction electrons. Now, when these in this state, in this particular state, that means when the potential difference is not applied and when the electrons are moving here, so we know that the electrons, the free electrons, will be moving, and and this movement or this motion depends upon the temperature, and this depends upon the temperature, and that's why, because this depends upon the temperature, it's called as thermal motion. So this depends upon the temperature, so that's why this motion is called as the thermal motion. Okay, now anyways here we understood here the free electrons are moving here and there, and we call them as the this motion as the thermal motion. Right now, when the potential difference is applied, or if you are connecting it to a source, any source, a cell or a battery or something else. Now, these electrons, these free electrons, will gain some energy and will be accelerating. That means here, so these free electrons will be accelerated. Why they are accelerated means because of the applied voltage or the potential difference. So they accelerated, that means they gain some energy. So here we understood that these particles are now set in the motion. So now when they are moving here, when these particles are moving here, so around these charged particles here, so the atoms of this conductor are present. So when these free electrons are moving after gaining some acceleration, that means gaining some energy, they collide with the atoms. So when they are moving, they collide with atoms. Usually when the collision takes place, suddenly after colliding, they will lose some energy. So after collision, they will lose energy. So now here, one thing we have to understand here, when they are moving, they will be gaining some velocity. And then the collision will take place. And after losing energy, again they will lose the velocity. After collision. Immediately after collision, they will lose some energy. And already it is up, the potential difference is applied. So now, because of this potential difference applied or the applied voltage here, they again gain the energy because of this. So after this, again they gain the energy. That means they are accelerated again, and again there will be velocity further. They will gain some velocity. And again, after gaining the velocity, again they will go and collide the atoms. After colliding the atoms, they will lose the energy. This process continues. So now from this we understood that. So now the free electrons, they will be going, colliding. They will be going, colliding. They will be going and colliding, and then they will be losing the energy. And they will gain the energy because of the potential difference applied. So in this process, what is happening means the velocity will be changing. So in here, anyways, the velocity is decreasing or increasing, we can consider the average velocity gained by the electrons, and this gaining is due to the applied voltage or potential difference. So this average velocity we will be calling as drift velocity. is called as drift velocity. Okay, now we were talking about this, the velocity, the average velocity. So look at here, before the potential difference is applied, the electrons were moving because of the temperature, and it depends on the movement depends upon the temperature, and we call this as the thermal motion. And here one more thing you can keep in mind: at room temperature, thermal velocity is 10 to the power of 6 meter per second. Okay, so anyways here, before the potential difference is applied, even though the motion is there, they are not the, what you call it as, the net flow is zero. Already know about this. The net flow is zero. So because the net flow is zero, no electric current is there in the conductor. No electric current is there in the conductor. Now coming to and the next situation is when you are applying the voltage, or potential difference is applied. Now, because of this applied voltage or the potential difference, these electrons will be accelerated. These free electrons will get accelerated and they gain energy. And because of gaining energy, they start moving. They gain some velocity, and they will go and collide with the atom of the conductor. After colliding with the atom of the conductor, certainly they will lose some energy and thereby loses the velocity. And again, because already we are applying the continuously, it is in what you call it as, the potential difference is applied. So again they get accelerated, will gain some velocity, and this process continues. So overall here, by losing energy, gaining energy, and whatever it is, the velocity is gaining or losing. So we can see an average velocity of an electron in this case. So the average velocity. So here we are considering this average velocity in the direction of the electric field. So average velocity in the direction of the electric field here. So the average velocity gained by the electron, the applied voltage, is the drift velocity. So this is an important term what we have to understand when we are talking about this current electricity, the drift velocity of the electrons. It is generated by Vd. Okay, now pause the video and take the screenshot of this. Okay, now we talked about the drift velocity, and usually they are denoted by V, but here we just keep in the mind as Vd, and we will just follow it as the Vd itself. Okay, now we want to find an expression for correcting this Vd electric current. And if we talk about electric current, automatically we can talk about the current density. So we want to find the expression for this. So for this, what we are going to do is very simple. You can understand very easily. So now let us take a conductor of length L and cross section A. Cross sectional area A. Okay, so now its length is L, and the area of cross section A, and number of electrons per unit volume is taken as N, and charge on an electron is E. Okay, so now first let us write what is the volume of the conductor. What is the volume of the conductor? Its length is L and cross sectional area is A, so it is L into A. So it is L into A. And if for unit volume it is, there are n number of electrons per unit volume. For total volume, number of electrons in the total volume is this. This is the total volume. For unit volume it is N, So it is N into L into A. So now let us find the total charge. Total charge. Here these many number of electrons are there. For each electron it is E. So it is E into N into L into A. This is the total charge. So total charge Q is given by E, or we can N, E, L, A. In whatever manner you want, you can write. No problem, no issue here. Right now, suppose if this, for this conductor, you are applying, if it is connected to a source, and if charge Q is provided, charge Q is provided, that means in any cross section, I current flows in time t. When this happens, if it is connected to a source which provides the Q charge, then you know from this Q is equal to I by T. Sorry, I is equal to Q by T. And I is equal to, so now what is Q here? N, E, L, length, A by T, time. And if we just look at this, this is distance by time, that is nothing but your speed or velocity, isn't it? The speed or velocity here, we are talking about the free electrons. The speed or velocity is nothing but the drift velocity, whatever we have learned up to now. This is the velocity where the electrons can move. So this is the drift velocity Vd. So now I is equal to N into E. So instead of this, I am going to write as Vd A. So now we got the expression for Vd and I, isn't it? So now if you just look into this expression, we can draw one more important thing from this. This is constant and the charge is constant and area of cross section of conductor is constant. So I is directly proportional to Vd. Keep this in your mind. It helps us in our numerical calculations or new applications. So the current in a conductor is directly proportional to the drift velocity. Okay, now here we got it as I is equal to N, E, A, V, T. Just we remember this, the formula in this form. I is equal to N, E, A, V, T. Why I am writing like this means in most of the books it will be, the formula will be like this. By looking at that you can easily identify. So NAVD, what is NAVD? It is the current. Okay. Right now, so now VD is equal to I by NEA. Just bringing this side, I by NEA. Why I am bringing here means here I want to just get this. What is I by A? It is J. VD is equal to J by NE. Or J is equal to VD NE. This is one more important expression. This is one important expression and this is another important expression, and this also we use this for the application part. So now we got the expression for the drift velocity. So how did we get this expression for drift velocity? Here we considered, as this derivation is important and you have to keep it in your mind. So here we are considering a conductor of length L of cross-sectional area A and number of free electrons in unit volume, not the complete volume, in unit volume it is N. And the charge of the electron is E, always denoted by E, you know that. So now, first what we are taking the volume of the, what is the volume of the conductor? It is the area of cross section into length, L. So what are the, in the unit, if in unit volume it is N, what is the total number of electrons present there? So total volume into the number of electrons per unit volume. So N into L into A. So what is the total charge? If the number of electrons are this much into E, this much means here we got this as N into L into A. So that much into E, N into L into A into E. So we got it here. The total charge is represented by Q. Now, if this conductor is connected to a source which provides the charge Q, if it is providing charge Q means the electric current should be there across any cross section. That electric current is denoted by I in some time interval t, crossing through that cross section t. So Q I T. So we know the expression connecting this Q I T. Q is equal to I T or I is equal to Q by T. So now I is equal to Q by T. Already we got it as NELA by T. So L by T, you know this. We learned this in our mechanics. L by T. It is distance by time or displacement by time. So displacement by time gives you the velocity. So NE, and this velocity here we are considering it as the drift velocity because we are talking about the motion of the free charges. That means the electrons here, that is called as the drift velocity. So NEVDA. So this N is constant, E is constant and A is constant. So the current in a conductor is always directly proportional to the drift velocity. The current in a conductor is always directly proportional to the drift velocity. So we just left it there. And so now here I am writing the expression in the remembering manner. I is equal to NEAVD. Just put it in your mind like that. I is equal to NEAVD. Okay? Right. VD is equal to I by just bring this side NEA because I want to extract J from there. So VD is equal to J by NE. So J is equal to VD NE. So this is the derivation and you can remember it easily. Okay? See you in the next session.